In this video, we'll look at the addition of oxygen and nitrogen nucleophiles to aldehyde and ketone carbonyls. Let's look at the addition of oxygen nucleophiles to aldehydes and ketones, specifically water and molecules of alcohol. A nucleophilic attack of water and alcohols to carbonyls of the aldehydes and ketones is reversible. Equilibrium will favor the carbonyl compound. However, you will form in solution a geminal diol from an aldehyde or ketone and water, or a hemiacetal from an aldehyde and ketone and a molecule of alcohol. So they'll form in solution, but you normally cannot isolate them, and you'll see them as mechanistic intermediates, transient intermediates in reaction mechanisms. Let's start with water. Remember, these are neutral conditions, so there's no acid added. If you remember from the first video, we looked at general reaction mechanisms, where you have a neutral nucleophile adding to an aldehyde or ketone under neutral or basic conditions. And the first step was nucleophilic addition to the carbonyl. I make a new oxygen and carbon bond with the pair of electrons on oxygen, and I break the pi bond of the carbonyl, and I end up making a new oxygen carbon bond. And notice now the oxygen has a positive charge, and this was the time when you can remove the proton from water. And we're having another molecule of water acting as a Lewis base. You end up now with an oxygen anion, which then picks up a proton from the protonated water. So notice that you've transferred a proton from this oxygen to this oxygen, and you're doing it in two steps. This is a two-step proton transfer. It's not jumping directly from this oxygen to this oxygen. It's going into solution. You end up with this. This is a true mechanistic intermediate. This then picks up the proton in a second step, and you have a geminal diol. The addition of alcohol, a molecule of an alcohol, to an aldehyde or ketone, it's basically the same mechanism that was proposed above. The only difference is that instead of HOH, we have ROH. So you can see the first step is nucleophilic addition, followed by the two-step proton transfer. Exactly the same mechanism, except that instead of HOH, we have ROH adding to the carbonyl. When you have a molecule that has an aldehyde or a ketone in the same chain as an OH group on a carbon in that chain, and you have the possibility of forming a 5 or 6 membered ring, in this case the equilibrium actually favors the ring, and you can isolate the products. So in this case we have an OH group at the end of this chain doing an intramolecular, that is within the same molecule. So intra means within the same molecule. Inter, I-N-T-E-R, would mean two different molecules which are unattached. So this is an intermolecular reaction. This is an intramolecular reaction. You have nucleophilic addition. Notice that the carbonyl has two faces, and so therefore if the oxygen attacked the front face, you would get this one. If it attacks the other face, you get this guy here. These are both enantiomers, so you're generating a new stereogenic center, a new asymmetric center. The same mechanistic steps that you saw above will happen down here. First step is nucleophilic attack. Second step is Lewis base removing a proton off of the nucleophilic oxygen. And we end up performing a two-step proton transfer from this oxygen to this oxygen, and we have a 5 or 6 membered cyclic hemiacetal. You'll encounter these in the chapter involving carbohydrates. We've seen that nucleophilic addition of alcohols to aldehyde and ketone carbonyls under neutral conditions affords unstable, unisolable hemiacetals. However, if you carry the reaction out between an alcohol and an aldehyde and a ketone, or a ketone, in the presence of an acid catalyst, you obtain stable isolable molecules called acetals. So don't think of it as an ether or a diether. It's its own functional group. It's called an acetal. And notice also that this carbon, it's attached twice to oxygen, is the same oxidation state as the original carbonyl. The carbonyl is also attached twice to oxygen. So this is neither a reduction or an oxidation. It's simply a functional group transformation. Let's propose a mechanism for this. This is a good problem for you to practice on. You can do this on your own before viewing the mechanism that's going to be shown here. Remember, I had indicated that a good approach to solving mechanism problems, especially as you're starting, is to make a list of bonds that need to be made or bonds that need to be and bonds that need to be broken. You'll see that in this particular reaction, we have to make 2 new carbon-oxygen bonds here that I'm highlighting. We also have to make 2 new oxygen-hydrogen bonds to this red oxygen. I've indicated that this red oxygen is derived from the oxygen of the carbonyl. This is to make it clear that it's this oxygen that's being lost as water and not one of the oxygens from a molecule of methanol. Therefore, if this red oxygen becomes water, you're going to have to break both the sigma and pi bond to oxygen. So this double bond has to be completely broken. And at some point in your mechanism, you'll see that you have to break the OH bonds as well, because here you see there's no H's attached to these OCH3s, whereas you have them in the starting material. So remember, we're making this list of bonds that need to be made and bonds that need to be broken in order to help you to start your mechanism or to help you as you work through your mechanism if you get stuck. Because if you don't know what to do first, you can go through each item and ask yourself, is this a reasonable thing to do? And you'll find that when you do this mechanism, there's only one reasonable thing to do to start with. What will also help you, besides this list, is if you remember the general mechanisms for the reactions that we're investigating. In this case here, it's nucleophilic addition to an aldehyde or ketone with a neutral nucleophile under acidic conditions. If you remember from video number 1 in this chapter, under acidic conditions, the first thing that you do is you protonate the carbonyl, and you do that before the nucleophilic attack. And that's because when you protonate the carbonyl, you make that carbonyl more electron poor. You make it a better electrophile, and that's illustrated by drawing this charge-separated Lewis structure, this poor Lewis structure. Again, it's just a gimmick or trick in order to establish the reactivity of polar molecules that have pi bonds. In this case here, we see that this carbonyl carbon is electron poor, and it can be attacked very readily by a nucleophile. So this is a better electrophile than the unprotonated carbonyl. You don't have to draw this when writing out your mechanism. I just did it here to illustrate the fact, or to emphasize the point, that this carbon is electron poor and is prone to nucleophilic attack. We can go ahead and do the nucleophilic attack, and you can see that when I do that, so already I made 1 OH bond, so I ticked that off on my list. When I have the nucleophilic attack occur, I'm making an oxygen-carbon bond, and I'm also breaking the carbon-oxygen pi bond, so I tick those off on my list. Remember that at some point in your mechanism, you're going to have to break a bond between the oxygen and hydrogen. We have to break these bonds. We didn't do it before the nucleophilic attack. We do it after the nucleophilic attack, because before the nucleophilic attack, this is a neutral oxygen, not very acidic. After the nucleophilic attack, oxygen has a positive charge. Therefore, we know that this OH bond is acidic. This was also shown in the generic mechanism on the first video. We have a Lewis base come by and take this proton away. And so now, when I do that, I end up with a hemiacetal. This mechanism up to this point, going from ketone to hemiacetal is similar to the mechanism that we saw already for the formation of a hemiacetal under neutral conditions. But remember, under acidic conditions, the difference between the two mechanisms is you make the OH bond first, and then second have the nucleophilic attack make this CO bond. What I'm doing now is, overall, I did a two-step proton transfer. Why did I do that? So remember, I'm taking the proton off of this oxygen, and I'm transferring it in two steps. Lost to solution, then transferred to this oxygen. I'm doing it because I want to make this oxygen a good leaving group. Remember, not only do I want to make two OH bonds, so here I have it, there you can actually see the molecule of water. I want to get rid of this oxygen. I have to break this carbon-oxygen sigma bond because this oxygen is completely lost from the carbonyl and it becomes water. By protonating it, I do both of those things. I make the OH bond and I allow this carbon-oxygen bond to break. So this will leave as water, and I'll end up with a mechanistic intermediate that looks like this. We know that this carbon is electron poor, much in the same way that this carbon is electron poor, and nucleophiles can attack it. So if a nucleophile can attack this carbon, the nucleophile being methanol, I can have another molecule of methanol doing a nucleophilic attack. And in this case here, you can see now I've made another carbon-oxygen bond. The last thing I have to do now is just break the OH bond in this second molecule of methanol that added to this carbon, and I end up now with the structure of the acetal. Notice the overall flow in this mechanism. The first step was proton transfer, followed by nucleophilic attack, followed by two-step proton transfer to the leaving group leaves, then a nucleophile comes in. You'll see that when we continue and look at further mechanisms, for example, the imine and enamine formation that we'll see shortly, many of the steps here will be reflected in those new mechanisms. If instead of treating an aldehyde or a ketone with two molecules of an alcohol under acidic conditions, you treat an aldehyde or a ketone with a single molecule that has two OH groups under acidic conditions, you will form an acetal, but it'll be a cyclic acetal. The mechanism for the formation of a cyclic acetal will be extremely similar to the mechanism that you just saw for the formation of an acyclic acetal. What you should do for this problem is attempt to propose a mechanism for the formation of this cyclic acetal from this ketone and this diol. The solution will be posted. The formation of acetals from aldehydes and ketones treated with diols or molecules of alcohol under acidic conditions is an equilibrium reaction. And equilibrium is driven to the right to the formation of an acetal by driving water away as it is being formed during the reaction, and according to Le Chatelier's principle, that would drive the equilibrium to the right. Your textbook shows the laboratory method that's used to remove the water. Since this is an equilibrium reaction, it's perfectly possible then to take an acetal and treat it with a large excess of water in the presence of an acid catalyst, and you would then convert it back by hydrolysis, cleavage by water. Hydrolysis, you would end up with the original carbonyl compound and diol or molecules of alcohol. So in this case here, hydrolysis of this acetal with excess water and H+ would give you these two molecules. What you should do as a practice problem is write out the mechanism for hydrolysis of this acetal, giving the original starting materials. You'll find that you will be using the same mechanistic intermediates that you used in the mechanism for its formation. The fact that this acetal is easily made from a carbonyl and that the acetal can be converted back to the carbonyl very easily, it makes it a good candidate for something which is called a protecting group. And that's a functional group that can be used temporarily to convert the original functional group to mask its normal reactivity. And an example of that is shown on the next slide. Suppose I needed this compound desperately to be used as a starting material in a chemical synthesis. And on the shelf, I had a bottle of this molecule that has an aldehyde and alkyl halide functional group. I might think that, well, maybe I can take this and I can treat it with this nucleophile. I know that this is a nucleophile that reacts with primary alkyl halides to make carbon-carbon bonds, and I can synthesize this compound in this fashion. Well, why is it that I can't do that? Why can't I perform this reaction without obtaining any major side products? And in this problem, we'll see that we can get around this by using protecting groups. Take a look at this molecule. It has 2 electrophilic carbons. We know that carbonyls can undergo nucleophilic addition, and we know that primary alkyl halides can undergo nucleophilic substitution. So if I treat this molecule with this carbon nucleophile, I'll have attack at both the carbonyl and also at the alkyl halide carbon. I don't want that. I only want attack at the alkyl halide carbon. But I remember that aldehydes and ketones can be converted to acetals. So it's possible for me to take this molecule and convert its aldehyde group to an acetal functional group. Now this molecule has only 1 electrophilic carbon. This nucleophile, this carbon nucleophile, will not attack the acetal carbon. There's no carbonyl here and there's no leaving group here. Therefore, when I treat this protected molecule, so this is called the protection step, I ended up with the protected molecule. If I treat it with the carbon nucleophile, an SN2 reaction occurs and I end up with the following compound. Remember that this acetal is a masked carbonyl compound. It's a carbonyl compound traveling incognito. It's masked. All I need to do now is just hydrolyze it. This is called the deprotection step. So putting the protecting group on is the protection step. The deprotection step is removing the protecting group. In this case here, it's just mild acid and water. And I end up hydrolyzing this and I get my aldehyde. So in this case here, I could only treat this compound, or I should say I could only convert this compound to this if I first protected the carbonyl before I did the nucleophilic attack. A final word about protecting groups. I discussed it here, your book discusses it, but it doesn't mean that you should always try to use protecting groups in your syntheses. The use of a protecting group adds 2 additional steps to a synthesis, protection and deprotection. The more steps in a synthesis, the lower the overall yield is going to be, and it's going to take more time and more money. So the best syntheses are the ones that avoid the use of protecting groups. And chemists these days are even trying to work out synthesis of complex polyfunctional molecules without the use of protecting groups. That's a hot research topic because of the fact that the more protecting groups you add, the more steps, the more time and money, the lower the overall yield. An example. Let's compare these two. We have one example where we have no protecting group, and we have an example where we're using just 1 protecting group. And let's assume that each step in both syntheses gives you a 90% yield. That's great. I mean, it would be great to have a 90% yield on every reaction I performed. So A is converted to B in 90%. Then I take B and I perform another reaction on it and I make C in 90%. So 90% of 90%, the overall yield is an 81% yield. with no protecting groups. Let's do the same thing, but have one protecting group added or involved in the synthesis. We take A, we convert it to protected A, 90% yield. I take my protected A, I perform my transformation to convert A to B in 90%. Now I have to remove the protecting group, 90% yield, and then lastly I convert B to C, much like I did above, and I get a 90% yield. But look at this, overall, 90% of 90% of 90% of 90%, 66% overall yield with 4 steps using a single protecting group. So you can imagine if you have syntheses that use 2, 3, 4 protecting groups, that's going to give you a much poorer overall yield of the desired product. So please remember that in your syntheses, if you're given an exam and you have to do a synthesis problem, or you're working on problems from the text or assigned problems that I give you, try to avoid the use of protecting groups. Only when the problem says, use a protecting group, or like in the previous example, I showed you that the only way that I could synthesize that compound from the starting material that I happen to have a bottle of it on the shelf was by using a protecting group. So please do not feel that you have to use a protecting group in your syntheses, and really pretty much all of the problems that you're going to be assigned can be, again, unless it's one that is asking you to use a protecting group, all the synthetic problems you're going to be assigned can be done without using protecting groups. Now let's look at nitrogen nucleophiles, specifically ammonia and amines, adding to aldehyde and ketone carbonyls, in this case forming imines and enamines. When it was oxygen nucleophiles, specifically alcohols, you ended up with stable acetals. In this case, when you use primary and secondary amines reacting with aldehydes and ketones, you'll end up with stable imines or enamines. In nucleophilic addition to carbonyls with neutral oxygen nucleophiles under acidic conditions, you would normally protonate the carbonyl before nucleophilic attack. That was with oxygen nucleophiles. However, with nitrogen nucleophiles, specifically ammonia and amines, nitrogen is more basic than oxygen. Therefore, under acidic conditions, the nitrogen is protonated and not the oxygen. So when you write out mechanisms involving nucleophilic attack on aldehydes and ketones under acidic conditions, first have the unprotonated carbonyl react with the nitrogen nucleophile. So nucleophilic attack occurs before protonation. In this case here, we end up with what can be called a hemiaminal intermediate. Remember the hemiacetals. And under acidic conditions, these hemiaminal intermediates will lead to stable compounds called imines and enamines, as shown on the following page. When aldehydes or ketones like cyclohexanone shown here are treated with primary amines in the presence of an acid catalyst, you form a species called an imine with a carbon-nitrogen double bond. When aldehydes and ketones are treated with secondary amines in the presence of an acid catalyst, you end up with a molecule that has both alkene and amine functionality called an enamine. The mechanisms for the formation of an imine and enamine are identical up to a point, after which they diverge. And you'll see that as we work through the mechanisms for the formation of these products, that some of the steps are very similar to the types of steps that you performed when converting an aldehyde or ketone to an acetal. Remember, under acidic conditions with a nitrogen nucleophile, the first step will not be protonation of the carbonyl, but nucleophilic attack by the amine on the carbonyl carbon. Once we do that, we can lose a proton off of the nitrogen. Remember, we do not lose the proton at this point. We lose it after we make the carbon-nitrogen bond because nitrogen has a positive charge. If we take these alkoxide anions and protonate them, we will have done overall a two-step proton transfer from nitrogen to oxygen. And we end up with hemiaminal mechanistic intermediates. So far the mechanisms are identical, the only difference being that we're using a primary amine for the formation of the imine and a secondary amine for the formation of the enamine. Like we did with hemiacetals in converting them to acetals, where we protonated the oxygen to make it a good leaving group, we'll do the same thing here. We have acid catalyst in solution, we'll protonate it, now the OH becomes a good leaving group. When it leaves, we can end up having nitrogen making a pi bond to carbon, and we end up with what are called iminium ions. Here we have an iminium ion that has hydrogen attached to nitrogen. All we have to do in this case is lose that hydrogen as a proton. The 2 electrons go to nitrogen, and you will have formed an imine. In the bottom case, we can lose a proton off of nitrogen. Oops, there is no hydrogen. There's no proton attached to nitrogen. Here we have methyl and hydrogen. Here we have methyl-methyl. Where can we lose a proton off of this iminium ion in order to form a stable neutral product, the enamine? Here's where these charge-separated Lewis structures come in handy. By drawing this poor Lewis structure, it reveals that this carbon, the one that's doubly bound to nitrogen here, is electron poor, and it acts like a carbocation. You know that carbocations can do 3 things. They can be trapped by nucleophiles, they can rearrange to carbocations of equal or greater stability, and also they can lose a proton on the carbon next door. In this case here, when we lose a proton on the carbon next door, we end up forming the double bond of the enamine. So notice how both of these mechanisms are identical up to this point, where the very last step, where we lose a proton. And also please notice that some of the steps that we're performing here, nucleophilic additions, 2-step proton transfers, protonating the leaving group to make it a good leaving group, are very similar to the mechanism for the formation of an acetal from aldehydes and ketones.